Imagine you could fast forward through time, not years, not centuries, trillions upon trillions of years into the future. You would witness something no human eye will ever see. The last star in the universe flickering out, the final photon of light radiating into an ocean of absolute darkness, the end of everything we recognize as existence. But here's what keeps cosmologists awake at night. We know exactly how it happens. We've mapped the timeline, we understand the physics, and the universe has already begun its descent into this cosmic oblivion. Right now, at this very moment, the universe is dying. The process is irreversible. The timeline is set, and the evidence surrounds us in every direction we look. What if I told you that the light from distant galaxies carries within it proof of our universal death sentence? That the very expansion of space itself is gradually extinguishing every source of energy, heat, and light? That we exist in a brief, brilliant moment before an eternity of absolute zero? Today, we journey through evidence that challenges everything we thought about the permanence of existence. We'll trace the universe from its violent birth to its inevitable heat death, a journey of Google years into a future of perfect, frozen stillness. Prepare yourselves. We begin. In 1998, two teams of astronomers made a discovery so shocking that it won them the Nobel Prize and sentenced the universe to death. The Supernova Cosmology Project and the High-Z Supernova Search Team were doing something that seemed straightforward, measuring the rate at which the universe's expansion was slowing down. Because, of course, it had to be slowing down. Gravity pulls everything together. The Big Bang might have flown matter apart initially, but gravity should be reeling it back in, gradually breaking the expansion like friction slowing a spinning top. They used Type 1a supernovae as their cosmic measuring sticks. These stellar explosions are remarkably consistent. Each one releases almost exactly the same amount of energy, making them perfect standard candles for measuring cosmic distances. By comparing how bright these supernovae appeared versus how bright they should be, astronomers could calculate precisely how far away they were. And by measuring their redshift, how much their light had stretched during its journey through expanding space, they could determine how fast the universe was expanding at different points in cosmic history. The teams expected to measure a decelerating universe. Instead, they discovered something impossible. The distant supernovae were dimmer than they should be, not by a little, by a significant, measurable amount. This could only mean one thing: they were farther away than expected. But how could that be? The answer sent shockwaves through cosmology. The universe isn't just expanding, it's accelerating, speeding up, as if some invisible force is pressing down on the cosmic accelerator, driving galaxies apart faster and faster with each passing moment. Imagine throwing a ball into the air and having it accelerate upward instead of falling back down. Imagine pushing a swing and having it go higher without you adding more force. This violated every intuition about how the universe should behave. They called this mysterious force dark energy, not because it's dark, we can't even detect it directly, but because we have no idea what it is, and it comprises roughly 68% of the entire universe. Dark energy permeates every cubic centimeter of space, and its pressure is negative, causing space itself to expand at an accelerating rate. Think about that. More than 2/3 of everything that exists is made of something we don't understand, and it's tearing the universe apart. But here's what makes this discovery a death sentence. Dark energy doesn't dilute as space expands. Unlike matter, which spreads thinner as the universe grows, dark energy appears to maintain constant density. As the universe doubles in size, the amount of dark energy doubles too. This means the acceleration never stops. It only intensifies. The universe has three possible fates, cosmologists realized. It could collapse back on itself in a big crunch. It could expand forever at a constant rate, gradually cooling. Or, and this is what the evidence showed, it could accelerate into oblivion. We're living in scenario 3. The implications are staggering. Every galaxy beyond our local cluster is moving away from us, and they're doing it faster each moment. Right now, the most distant observable galaxies are receding at velocities approaching the speed of light. In the future, they'll cross an invisible boundary called the cosmic event horizon and disappear from view forever, their light stretched into infinite wavelengths, becoming unreachable by any means. Let me put this in perspective. The Andromeda galaxy is currently rushing toward us at 110 kilometers per second. It will collide with the Milky Way in about 4.5 billion years, creating a magnificent merger that astronomers have named Milkomeda. This will be one of the last great cosmic events in our corner of the universe. But almost every other galaxy we can see is racing away. The Virgo cluster, 60 million light-years distant, recedes at 1,200 kilometers per second. The Coma cluster, 320 million light-years away, flees at 7,000 kilometers per second. The farther out you look, the faster they retreat. Within 1 trillion years, every galaxy beyond our local group will have accelerated beyond the cosmic event horizon. Future astronomers living in the merged Milkomeda galaxy will look up at a night sky containing only the stars of their own galaxy, surrounded by perfect darkness. They'll have no evidence that billions of other galaxies ever existed. The entire observable universe will shrink to a single island of light in an expanding ocean of void. But the evidence forces us to confront an uncomfortable possibility. This is just the beginning of the end. The heat death of the universe isn't some distant abstraction. It's a physical inevitability written into the fundamental laws of thermodynamics. And the accelerating expansion discovered in 1998 means it will be absolute, total, irreversible. The second law of thermodynamics is brutal in its simplicity. Entropy always increases. Order becomes disorder. Hot things cool down. Energy disperses. And once it's dispersed evenly throughout a system, nothing interesting can happen anymore. The universe is that system, and we can watch it dying in real time. In 2014, an international team of astronomers used multiple telescopes to measure the total energy output of the universe across different wavelengths. They combined data from the Galaxy and Mass Assembly project with observations from ultraviolet to far infrared wavelengths. Their conclusion was unambiguous. The universe is producing half the energy it did 2 billion years ago. Half in just 2 billion years. That's only 14% of the universe's current age. Scientists discovered this by measuring the light from over 200,000 galaxies. They found that star formation has declined by 97% since its peak 11 billion years ago. The universe used to create stars at a prodigious rate, turning vast clouds of hydrogen and helium into brilliant fusion reactors at a pace we can't barely imagine. Now, that age of stellar creation is ending. The Milky Way forms roughly 7 new stars every year. During the universe's peak star formation era, galaxies were creating hundreds of new stars annually. Some starburst galaxies reached rates of thousands per year. Those glory days are over. Current observations show that galaxies are running out of the cold gas needed to form stars. The intergalactic medium is being heated by quasar winds and supernova feedback, making it harder for gas to collapse under gravity. Dark energy stretches space faster than new material can accumulate. The cosmic assembly line is shutting down. But this represents just one piece of a much larger puzzle hidden in the cosmic microwave background. The CMB, that faint afterglow of the Big Bang, tells us something profound about where we are in cosmic history. When the universe was 380,000 years old, it had a temperature of about 3,000 Kelvin, hot enough to glow. The entire cosmos was filled with a warm orange light. Today, that same radiation has cooled to 2.725 Kelvin, just 2.725 degrees above absolute zero. The expansion of space has stretched those ancient photons, redshifting them from visible light into microwaves. We're living in a universe that has already cooled by 99.9%. And it's still cooling. Every moment, the temperature drops infinitesimally. In another trillion years, the CMB will have cooled to less than 0.003 Kelvin. Eventually, it will approach but never quite reach absolute zero. The evidence extends beyond temperature measurements into the realm of matter itself. The Planck satellite mapped the distribution of matter and energy across the entire observable universe with unprecedented precision. What it revealed was a cosmos in which dark energy has already achieved dominance. 13.8 billion years ago, at the moment of the Big Bang, the universe was pure energy. As it expanded and cooled, that energy condensed into matter, first into fundamental particles, then into atoms, eventually into stars and galaxies. For billions of years, matter dominated. Gravity sculpted the universe into the cosmic web we observe today, vast filaments of galaxies surrounding enormous voids. But roughly 5 billion years ago, something changed. Dark energy became the dominant force. Its repulsive pressure began overwhelming gravity on cosmic scales. The expansion, which had been decelerating, began to accelerate. Galaxy clusters stopped forming. The large-scale structure of the universe froze into place. We can observe this transition in the clustering patterns of galaxies. Surveys like the Sloan Digital Sky Survey have mapped the three-dimensional positions of millions of galaxies. By analyzing how they cluster together, cosmologists can measure the strength of gravity versus dark energy throughout cosmic history. The data shows that cosmic structure formed hierarchically, small objects first, then progressively larger ones until about 5 billion years ago. Since then, the universe's largest structures haven't grown. Dark energy won. This isn't just about galaxies drifting apart. It's about the fundamental architecture of existence being locked into a configuration that will never change, only disperse. The most remarkable discovery involves what happens to the fabric of space-time itself as the universe ages. In 2016, researchers at the University of Oxford published calculations showing that dark energy doesn't just accelerate the expansion, it fundamentally alters the causal structure of the universe. As space expands faster and faster, the cosmic horizon shrinks. This is the boundary beyond which events can never influence us, no matter how long we wait. Right now, our cosmic horizon sits at about 16 billion light-years. Anything happening beyond that distance will never be observable from Earth, even in principle, because the space between us is expanding faster than light can traverse it. And every second, this horizon gets slightly closer. Think about what this means. The observable universe, the sphere of space from which light has had time to reach us, is actually shrinking in terms of what can causally interact with us. We're being progressively isolated from the rest of reality. Scientists discovered additional evidence in the behavior of photons themselves. Every photon loses energy as it travels through expanding space. This isn't absorption. There's nothing to absorb it. The expansion literally stretches the wavelength, reducing the photon's energy in the process. The oldest photons in the universe, those from the cosmic microwave background, have lost 99.97% of their original energy. They started as visible light and have been redshifted into microwaves. In the far future, they'll be redshifted into radio waves, then into wavelengths longer than galaxies, eventually becoming undetectable by any conceivable technology. This process is irreversible. Every photon in the universe is slowly bleeding out its energy into the expansion of space itself. The universe isn't just running out of new energy sources, it's actively degrading the energy that exists. Recent observations from the Dark Energy Survey have revealed something even more unsettling. Dark energy appears to be strengthening, or more precisely, we can't rule out that it might be. If dark energy is truly a cosmological constant, a fixed property of empty space, then its density remains constant while the universe expands. But some measurements suggest it might be quintessence, a dynamic field that could change over time. If dark energy strengthens, the acceleration could intensify beyond current predictions. This leads to a scenario physicists call the Big Rip. Instead of a gradual heat death over Google years, the universe could tear itself apart in just 22 billion years. The acceleration would become so extreme that it would overcome not just gravity, but eventually the electromagnetic and nuclear forces holding matter together. First, galaxy clusters would dissolve, then galaxies, then star systems, then planets, then atoms. Everything would be shredded by the expanding space between its constituent parts. Current evidence slightly favors the cosmological constant interpretation, meaning we're headed for heat death rather than the Big Rip. But the uncertainty reveals just how much we don't understand about the force determining our ultimate fate. The evidence extends beyond expansion into the realm of information itself. Black holes, those gravitational prisons from which nothing escapes, will eventually dominate the universe. When all the stars have died, black holes will be the last remaining massive objects, and even they aren't eternal. Stephen Hawking discovered that black holes emit radiation due to quantum effects at their evidence horizons. This Hawking radiation causes black holes to slowly evaporate, converting their mass into energy over incomprehensible timescales. A black hole with the mass of the Sun would take 10 to the 67 years to evaporate completely. The supermassive black hole at the center of our galaxy would take 10 to the 100 years. But they will evaporate, and when the last black hole vanishes in a final burst of radiation, the universe will have lost its last concentrated source of energy. All that will remain is a thin soup of photons and fundamental particles spread across an exponentially expanding void, approaching absolute zero. The most disturbing evidence comes from thermodynamic calculations about what happens after even the black holes are gone. The universe will enter what physicists call the dark era, followed by the photon age, and finally the eternal darkness. In the dark era, lasting from about 10 to the 40th to 10 to the 100th years from now, the only objects will be black holes, dead stars, and planets floating in absolute darkness. No light, no heat, just cold, dense objects slowly spiraling towards black holes through gravitational radiation. In the photon age, from 10 to the 100th to 10 to the 150th years from now, even the black holes will have evaporated. Only photons and leptons will remain, their wavelengths stretched to the size of galaxy superclusters, their energy infinitesimal, approaching but never reaching zero. After that comes eternal darkness, a universe expanded to infinity, cooled to near absolute zero, with its constituent particles so far apart that they might never interact again. Perfect equilibrium, maximum entropy, the heat death of the universe, complete and absolute. The evidence forces us to confront what it means for a universe to end not with a bang, but with an infinite whimper. The theoretical framework that unifies all this evidence comes from thermodynamics and general relativity working in concert. Einstein's equations describe how matter and energy curve spacetime. The laws of thermodynamics govern how energy flows and disperses. Together, they paint an unambiguous picture of cosmic decline. The second law of thermodynamics states that the entropy of a closed system always increases. The universe is the ultimate closed system. There's nothing outside it exchanging energy. Therefore, the universe's total entropy must increase until it reaches maximum, a state of perfect equilibrium where no energy gradients exist to drive any process. This isn't philosophical speculation. We can calculate it. Dr. Brian Greene, physicist at Columbia University, has described the universe's entropy budget in stark terms. The Big Bang began in an extremely low entropy state, all the energy compressed into an infinitesimal volume, highly ordered, far from equilibrium. The subsequent expansion has been a 13.8 billion-year journey toward disorder. Stars are entropy engines. They convert ordered nuclear fuel into disordered radiation. Every photon emitted by every star increases the universe's total entropy. Black holes are even more efficient entropy generators. The entropy of a black hole is proportional to its surface area, and supermassive black holes have entropies larger than anything else in the universe. When stars form from collapsing gas clouds, they locally decrease entropy by creating order. But the process releases so much heat and radiation that the universe's net entropy increases dramatically. Every structure we see, every galaxy, every star, every planet, is a local pocket of order purchased at the cost of vastly increased entropy elsewhere. This forces us to reconsider fundamental assumptions about the nature of time itself. Why does time flow forward? Why do we remember the past but not the future? The answer, many physicists believe, lies in entropy. Time's arrow points in the direction of increasing entropy. We perceive cause preceding effect because causes are lower entropy states and effects are higher entropy outcomes. In a heat-death universe at maximum entropy, would time still exist? If there are no processes, no changes, no energy gradients, would there be any meaningful difference between past and future? Some theorists argue that time itself might effectively cease in the final state of the universe, not because time stops, but because nothing happens to mark its passage. The implications are profound. The universe's death isn't just the end of stars and galaxies, it might be the end of time as a meaningful concept, the end of causality, the end of change itself. Leading physicists like Roger Penrose have proposed exotic possibilities for what might come after heat death. Penrose's conformal cyclic cosmology suggests that when the universe reaches maximum entropy and contains only massless particles, it might become mathematically equivalent to a new Big Bang. The end becomes the beginning, and the cycle repeats eternally. Other researchers, like Dr. Laura Mersini-Houghton at the University of North Carolina, investigate whether the universe might allow to tunnel from a high-entropy state into a new low-entropy state, essentially rebooting existence through quantum fluctuation. These ideas remain speculative. The mainstream scientific consensus is that heat death is final, total, a one-way journey into the void. But we don't have to wait Google years to observe the universe's decline. We're watching it happen now, and future observations will map each stage of cosmic death with increasing precision. The James Webb Telescope, launched in 2021, is already observing the most distant galaxies ever seen, galaxies as they appeared just a few 100 million years after the Big Bang. These observations reveal a universe in its youth, vigorous, violent, forming stars at prodigious rates. By comparing these early galaxies to nearby ones, we can measure exactly how star formation has declined over cosmic history. Future missions will extend this timeline. The proposed LUVOIR telescope, Large UV Optical IR Surveyor, could observe galaxies out to redshifts of Z equals 20 or higher, seeing the universe when it was barely 200 million years old. By mapping the complete history of star formation from the dawn of time to today, we'll create a detailed timeline of the universe's energy output and its decline. Recent breakthroughs in gravitational wave astronomy offer another window into cosmic evolution. When LIGO detected the collision of two black holes in 2015, it opened an entirely new way to observe the universe. Future gravitational wave observatories like LISA, Laser Interferometer Space Antenna, will detect the mergers of supermassive black holes across cosmic history. These observations will map the population of black holes, the universe's ultimate entropy sinks, throughout time. We'll watch as stars die and leave behind black hole remnants. We'll observe as those black holes merge into progressively larger ones. We'll create a census of the mass locked in these inescapable prisons, mass that will persist for 10 to the 67 years or more before finally evaporating through Hawking radiation. The Nancy Grace Roman telescope, scheduled to launch in the mid-2020s, will conduct the most comprehensive survey of dark energy ever attempted. By measuring the positions and redshifts of hundreds of millions of galaxies, it'll constrain the properties of dark energy to unprecedented precision. We'll finally determine whether dark energy is truly constant or evolving, whether we're headed for gradual heat death or catastrophic Big Rip. What scientists are building is nothing less than a complete thermodynamic ledger of the universe. How much energy existed at the Big Bang? How is it being dispersed? At what rate? Where will it end up? The Planck satellite measured the CMB temperature to be 2.72548 plus or minus 0.00057 Kelvin. That precision allows us to calculate exactly how much thermal energy remains in this primordial radiation field. It's about 4.17 times 10 to the minus 13 joules per cubic meter. Barely anything, yet it fills all of space. Future CMB missions will measure temperature fluctuations at even finer scales, revealing the detailed thermodynamic history of the universe from the Big Bang to today. We'll map every major energy transaction, the formation of the first stars, the reionization of hydrogen, the assembly of galaxies, the growth of black holes, and we'll project these trends forward, calculating with increasing confidence exactly when the last star will form, when it will die, when the last black hole will evaporate. The most sobering calculations involve what happens to complex structures in the universe's future. A team at the University of Michigan published projections in 2019 showing that Milkomeda, the merged Milky Way and Andromeda, will be the last place in our cosmic neighborhood where stars form. About 100 billion years from now, Milkomeda will exhaust its supply of hydrogen gas. The last star, probably a small red dwarf, will form. Then stellar creation in our corner of the universe will cease forever. These red dwarfs burn slowly, efficiently. The smallest ones could shine for 10 trillion years, 1,000 times longer than the current age of the universe. They'll be the last sources of starlight, the last warm places in an increasingly cold cosmos. When the last red dwarf finally exhausts its fuel and fades to a black dwarf, a cold, dead cinder of crystallized carbon and oxygen, the stelliferous era will end. No more stars, no more light, just darkness, interrupted only by the occasional flash as dead stars collide or fall into black holes. That's what we've condemned ourselves to understanding, the knowledge that everything ends, the knowledge that we can't stop it, the knowledge that the universe is dying and we're witnesses to its decline. The most profound implications emerge when we consider what heat death means for the possibility of life, intelligence, and consciousness in the universe's far future. In 1979, physicist Freeman Dyson published a remarkable paper titled Time Without End, in which he explored whether life could persist indefinitely in an expanding universe. His conclusion was cautiously optimistic. If intelligence could adapt to progressively lower energy states and longer timescales, it might be possible to sustain thought indefinitely, even as the universe approached heat death. Dyson imagined civilizations that hibernated for exponentially longer periods, waking briefly to think a few thoughts, then sleeping again as the universe cooled. By carefully rationing energy and accepting ever slower metabolisms, life might persist not just for billions, but for trillions of years. But Dyson's calculations were performed before the discovery of dark energy. The accelerating expansion changes everything. In an accelerating universe, the cosmic event horizon shrinks over time. This means the total amount of energy accessible to any civilization is finite, not infinite. Once galaxies accelerate beyond the horizon, their energy becomes unreachable forever. No matter how efficiently a civilization uses its resources, it will eventually run out. Dr. Lawrence Krauss at Arizona State University has calculated that even the most advanced civilization, capable of extracting every joule of usable energy from every star within its cosmic horizon, would face an absolute endpoint. The lights go out, the thinking stops, consciousness ends. This presents us with what philosophers call the ultimate tragedy of existence. Intelligence arose in a universe destined to snuff it out. We're like bacteria in a petri dish, evolved just in time to discover that we're living on a finite resource that's rapidly being exhausted. But perhaps the most disturbing questions involve not just the end of life, but the end of information itself. The holographic principle in quantum mechanics suggests that information, in some fundamental sense, cannot be destroyed. When a book burns, the information in it isn't lost, it's just scrambled into heat and ash. In principle, with perfect knowledge of every particle, you could reconstruct the book. Black holes challenged this principle. Information that falls into a black hole seems to be lost forever, destroyed behind the event horizon. Stephen Hawking's discovery that black holes evaporate through Hawking radiation created a paradox. If the radiation is purely thermal, random, then the information that fell in is truly destroyed, violating quantum mechanics. The resolution to this paradox, still debated, suggests that information is somehow encoded in the Hawking radiation. It's not destroyed, just scrambled beyond any practical ability to decode. But what happens in heat death? When the universe reaches maximum entropy and perfect equilibrium, all information becomes completely randomized. The state of the universe becomes the simplest possible description: empty space at nearly absolute zero. Every detail of cosmic history, every star that ever shone, every planet that ever formed, every thought that was ever thought, becomes irrecoverable even in principle. The universe doesn't just forget its past ceases to exist in any meaningful sense. What scientists are confronting is the ultimate consequence of the second law of thermodynamics, not just the heat death of matter and energy, but the information death of the universe itself. Everything that ever happened will be erased, leaving only a featureless void. Some physicists speculate about scenarios that might avoid this fate. Perhaps our universe is just one bubble in an infinite multiverse, and new universes are constantly being born through quantum fluctuations. Perhaps the laws of physics themselves evolve, and heat death is merely a phase transition to a different kind of existence we can't imagine. But these ideas, while fascinating, remain untestable. All the evidence we can actually observe points to the same conclusion. This universe had a beginning, it has a middle, and it will have an end. The question that haunts cosmologists is whether this truth diminishes existence or makes it more precious. We live in the brief moment when stars shine, when planets harbor life, when intelligence can contemplate the cosmos. Before us was only simplicity. After us will be only silence. The most mind-bending implication of all might be this: we exist during what is, thermodynamically speaking, the most interesting time in the universe's history. The ratio of current time, 13.8 billion years, to the time until heat death, 10 to the 100 plus years, is incomprehensibly small. We're seeing the universe in its first instant, before the unimaginably long decline into darkness. Why should we exist now? Why not in the early universe, before stars formed? Why not in the far future, among the dying embers of the last red dwarfs? The fact that we find ourselves in this brief window of cosmic complexity is either an extraordinary coincidence or suggests something profound about the nature of consciousness itself. Perhaps consciousness can only emerge in systems far from equilibrium, where energy gradients allow for the complex information processing we call thought. Perhaps we exist now because now is the only time we can exist, when the universe is old enough to have formed complex chemistry, but young enough to power it. In which case, we're not just observers of the universe's death, we're its only witnesses. The universe became conscious just in time to watch itself die. We began this journey with a simple question: what happens when the last star dies? Now we understand that it's not a simple question at all. The death of the last star is just one milestone in a thermodynamic journey that spans a googol years. A journey from perfect order at the Big Bang to perfect disorder at heat death. We've seen the evidence: the accelerating expansion discovered in 1998, the declining star formation rates measured across cosmic history, the inexorable cooling of the cosmic microwave background, the rising dominance of dark energy, the ultimate evaporation of black holes through Hawking radiation. We've traced the timeline: red dwarfs fading after 10 trillion years, black holes evaporating after 10 to the 100 years, the final photons redshifting into undetectability as the universe expands toward infinity. And we've confronted the implications: the end of light, the end of time, the end of information itself. The current scientific consensus is unambiguous. The universe is dying. Not might be dying, is dying. The process is underway. The timeline is set. The evidence is overwhelming. But here's what gives me hope. We figured this out. A species of primates on a small planet orbiting an ordinary star in an unremarkable galaxy looked at the light from distant supernovae and deduced the ultimate fate of everything. We measured the temperature of the cosmic microwave background to 5 decimal places. We calculated the evaporation time of black holes a googol years in the future. We are the universe understanding itself. For a brief moment in cosmic history, matter organized itself into structures complex enough to contemplate the whole. The universe is vast. Its death will be slow. Between now and then, there's time for countless stories, infinite experiences, discoveries we can't imagine. The fact that the stars will eventually die doesn't diminish their light now. If anything, their impermanence makes them more beautiful. We are the universe's way of bearing witness to its own magnificent temporary existence. The lights will go out, but for now they still burn, and we are here to see them shine. The universe is dying, the mysteries are endless, the journey continues. But we're not done, because there's a chapter in this story that deserves our attention, a chapter that spans trillions of years and reveals just how tenacious the universe's light will be before it finally surrenders to darkness. The stelliferous era, the age of stars, began roughly 100 million years after the Big Bang, when the first protostars ignited in clouds of primordial hydrogen. We're still living in this era, but its end is already written in the physics of stellar evolution, and the timeline is more specific than you might imagine. In 2012, astronomers at the Harvard-Smithsonian Center for Astrophysics published detailed models of the universe's stellar future. They calculated that within 100 trillion years, that's 100,000 billion years, the last conventional star will form from the last available reserves of hydrogen gas. 100 trillion years sounds unimaginable, but consider this. The universe is currently 13.8 billion years old. The stelliferous era will last roughly 7,000 times longer than the universe has existed so far. We're living at the very beginning, in the first 0.014% of the age of stars. But here's where it gets strange. Not all stars burn equally. A massive blue supergiant exhausts its fuel in just a few million years, exploding as a supernova in a spectacular death. Our Sun, a medium-sized yellow dwarf, will shine for about 10 billion years total. But the smallest stars, red dwarfs with just 7.5% the mass of the Sun, burn so slowly, so efficiently, that they can continue fusing hydrogen for 10 trillion years. 10 trillion years. Let that number settle in your mind. The oldest red dwarfs in existence today formed perhaps 13 billion years ago. They've barely begun their lifespans. They're cosmic infants that will outlive everything. These dim, cool stars, invisible to the naked eye, unremarkable in every way, will be the universe's last beacons of light. Scientists discovered something remarkable about these stellar survivors. They're completely convective. Unlike the Sun, which has distinct layers, red dwarfs churn their entire mass like a pot of boiling water. This means they can access all their hydrogen fuel, not just the material in their cores. They're the most efficient fusion reactors nature has ever produced. The most remarkable finding involves what happens when these red dwarfs finally die. Because they burn so slowly and completely, they don't explode. They don't puff off their outer layers like the Sun will. They just fade. Over billions of years, a dying red dwarf transitions from red to orange to yellow, growing hotter but dimmer as it exhausts the last of its fuel. Eventually, fusion ceases entirely. The star contracts under gravity, heating up one final time through compression, glowing white-hot briefly before beginning its long, slow cooling into darkness. What's left is called a black dwarf, a stellar corpse made of helium, carbon, and oxygen, no longer generating energy, simply radiating away its residual heat into space. But here's the cosmic irony that keeps physicists up at night. Black dwarfs are entirely theoretical. None exist yet. None can exist yet. The universe isn't old enough. The cooling time for a white dwarf to become a black dwarf is longer than the current age of the universe. Dr. Matthew Kaplan at Illinois State University calculated in 2020 that the first black dwarfs won't appear for at least 10 quadrillion years. That's 10 to the 15 years, roughly 700,000 times longer than the universe has existed so far. We're living in a universe so young that it hasn't produced a single completely dead star yet. Every white dwarf still glows, still radiates. The corpses are still warm. This means something profound. When we look at white dwarfs in the night sky, and there are estimated to be 10 billion of them in our galaxy alone, we're looking at objects that will outlast almost everything. They'll be here long before Earth is gone, long before the sun has died, long before the last conventional stars have faded. They're the universe's most durable monuments, silent, cooling embers floating in the darkness, taking quadrillions of years to finally grow cold. But the evidence suggests that even these eternal embers aren't truly permanent. After the last red dwarf dies and the last white dwarf cools, the universe will enter what cosmologists call the degenerate era. This is when the only significant objects in the cosmos will be stellar remnants, white dwarfs, neutron stars, and black holes floating in expanding darkness. This era lasts from approximately 10 to the 15 years to 10 to the 40 years after the Big Bang. That's 10 followed by 40 zeros. To put this incomprehensible number in perspective, if each atom in your body represented 1 year, and you represented the entire Earth, and the entire Earth represented the Milky Way galaxy, you still wouldn't have enough atoms to count the years in the degenerate era. During this time, the universe will be unimaginably cold, dark, and empty. The cosmic microwave background will have cooled to less than a billionth of a degree above absolute zero. Space will have expanded so much that the distance between objects will be measured not in light years, but in light millennia, light epochs, distances for which we don't even have words. What scientists found challenged everything we thought about stability. Even these dead stellar remnants aren't truly stable over such timescales. They decay through processes so slow they're essentially frozen in time by human standards, but given trillions of years, they become inevitable. Proton decay is the primary suspect. The standard model of particle physics doesn't predict that protons decay, but many grand unified theories suggest they must, given enough time. If protons decay with a half-life of 10 to the 37 years, a number constrained by current experimental limits, then even stellar remnants will gradually dissolve into radiation. Imagine it, a white dwarf the mass of the Sun, composed of approximately 10 to the 57 atoms. Each atom contains protons. If those protons decay, the entire star slowly transforms into a diffuse cloud of positrons, neutrinos, and gamma rays, spreading across an ever-expanding volume of space. A neutron star, that impossibly dense object with the mass of the Sun compressed into a sphere 20 kilometers across, would suffer the same fate. Its neutrons, normally stabilized by intense gravity, would decay into protons. Then those protons would decay further. The entire star would evaporate into radiation over timescales of 10 to the 40 years. Recent observations from the Super Kamiokande detector in Japan have placed the strongest constraints yet on proton decay. They've monitored 50,000 tons of ultra-pure water for over 2 decades, watching for the characteristic flash of light that would signal a proton's death. They've seen nothing, which means proton half-life must exceed 10 to the 34 years. But the absence of detection doesn't mean it won't happen. It just means it happens incredibly slowly. And in the deep future of the universe, incredibly slowly is fast enough. Even if protons are perfectly stable, if they simply don't decay, stellar remnants still face destruction through quantum tunneling and eventual collapse into black holes through a process called gravitational clustering. The evidence suggests that nothing solid survives forever. White dwarfs will either evaporate through proton decay or gradually accrete into larger objects that collapse into black holes. Neutron stars face the same fate. Even planets, frozen, airless, orbiting long-dead stars, or floating freely through intergalactic space, will eventually dissolve or be consumed. Dr. Fred Adams and Dr. Gregory Laughlin at the University of Michigan published extensive calculations in their book, The 5 Ages of the Universe. Their conclusion was unambiguous. Solid matter has an expiration date. Given enough time, everything either decays into radiation or gets crushed into black holes. By 10 to the 40 years from now, the universe will contain only 2 types of objects: diffuse radiation fields with wavelengths stretched to cosmic scales, and black holes, ranging from stellar mass holes of a few solar masses to the supermassive behemoths of 10 billion solar masses or more that once anchored galaxy cores. And then comes the black hole era, when these gravitational prisons become the last major structures in existence. But even they aren't eternal. In 1974, Stephen Hawking made a discovery that shocked the physics community. Black holes aren't entirely black. Through quantum effects at the event horizon, they emit radiation and gradually lose mass. Given enough time, every black hole will evaporate completely. This wasn't just theoretical speculation. Hawking derived it from first principles, combining quantum field theory with general relativity in a way no one had done before. His equations showed that the vacuum of space near a black hole's event horizon isn't truly empty. It's filled with quantum fluctuations that constantly create particle-antiparticle pairs. Normally, these pairs annihilate immediately, but at the event horizon, something remarkable happens. One particle falls into the black hole while its partner escapes into space. To an outside observer, the black hole appears to be emitting radiation, and because energy must be conserved, this radiation comes at the expense of the black hole's mass. The black hole evaporates, slowly, imperceptibly slowly, but inevitably. But here's what makes this process cosmically significant. The rate of evaporation depends inversely on the black hole's mass. Massive black holes evaporate slowly. Tiny black holes evaporate quickly. In fact, the temperature of Hawking radiation is inversely proportional to mass. A black hole with the mass of the Sun has a Hawking temperature of about 60 nanokelvins, 60 billionths of a degree above absolute zero. It emits energy at such a minuscule rate that it would take 10 to the 67 years to evaporate completely. 10 to the 67 years. That's 100 million trillion years, a number so large that if you tried to write it out in full, you'd need more particles than exist in the observable universe just to record the zeros. The supermassive black hole at the center of the Milky Way, Sagittarius asterisk, with a mass of 4 million suns, would take even longer, approximately 10 to the 100 years. That's a Google years. The largest black holes ever discovered, approaching 100 billion solar masses, would persist for 10 to the 106 years or more. Scientists discovered something profound about these timescales when they compared them to the accelerating expansion of the universe. Remember that dark energy is driving galaxies apart faster and faster. The cosmic event horizon, the boundary beyond which events can never influence us, is shrinking. This creates a cosmic loneliness. Each black hole will eventually find itself completely isolated, separated from all other black holes by expanding space. No matter how long they exist, they'll never collide, never merge, never interact. Each one will evaporate alone in an exponentially expanding void. Dr. Don Page at the University of Alberta calculated the detailed evaporation curves for black holes of various masses. What he found was that the process isn't gradual and steady, it accelerates dramatically near the end. For most of its lifetime, a black hole loses mass imperceptibly slowly. A solar mass black hole emits less than an attowatt of power. That's 10 to the minus 18 watts, a billion times dimmer than a firefly. You could wait 1 trillion years and barely measure any change in its mass. But as it shrinks, something remarkable happens. The Hawking temperature increases, the evaporation accelerates. In its final moments, a black hole becomes a blazing furnace, emitting more energy than it did during the previous eons of its existence. The last second of a black hole's life releases more energy than the previous trillion years combined. The final instant is an explosion, a burst of gamma rays carrying the last remnants of mass energy back into space. This final flash is called a Hawking explosion. It's the last gasp of the last structures in the universe. And then, nothing. Just radiation, expanding into infinite space. Imagine witnessing that moment, the last black hole in existence, floating alone in an incomprehensibly vast void, suddenly flaring into brilliance for a fraction of a second before vanishing forever. The universe's last firework, the final goodbye from gravity itself. But the evaporation of black holes raises one of the most profound questions in physics. What happens to the information that fell into them? When you burn a book, the information isn't destroyed, it's just scrambled into heat and ash. The laws of quantum mechanics insist that information cannot be destroyed. It can be scrambled, spread out, made practically irretrievable, but never truly destroyed. This is called unitarity, and it's fundamental to how quantum mechanics works. But black holes seem to violate this principle. When information falls past the event horizon, it's gone from the external universe. And if the black hole evaporates through Hawking radiation that's purely thermal, completely random, with no encoded information, then that information is destroyed forever. This is the black hole information paradox, and it's one of the deepest unsolved problems in theoretical physics. The most remarkable recent development involves what physicists call the Page curve. Don Page calculated that if information is somehow preserved, there should be a specific pattern to how it emerges from an evaporating black hole. Early in the evaporation, the Hawking radiation should be essentially random, but past a critical point, roughly when the black hole has lost half its original mass, the radiation should start carrying information about what fell in. By the time the black hole completely evaporates, all the information should have been encoded in the radiation, impossibly scrambled, but theoretically recoverable. In 2019, a team of physicists including Ahmed Almairi, Netta Engelhardt, Donald Marolf, and Henry Maxfield published calculations suggesting that the Page curve might be correct. Using new insights from string theory and quantum gravity, they showed how information might be preserved through subtle correlations between the Hawking radiation and the black hole's interior. Their work suggests that information isn't destroyed, but retrieving it would require measuring every particle of Hawking radiation with perfect accuracy, tracking quantum correlations across timescales of 10 to the 67 years or more, and performing calculations of incomprehensible complexity. Practically impossible, but theoretically preserved. What scientists are grappling with is the ultimate fate of information in the universe. If information is truly preserved through black hole evaporation, then in principle, the entire history of the universe, Every star that ever formed, every planet, every civilization, if any others exist, is encoded in the final radiation field filling the cosmos after the last black hole evaporates. It's all there. Every thought ever thought, every photon ever emitted, every quantum interaction since the Big Bang, all scrambled into a near-uniform sea of low-energy radiation with wavelengths measured in light years, but preserved nonetheless. This presents a strange kind of immortality. Nothing is forgotten, nothing is lost, but nothing can be reconstructed either. It's like having a library where every book has been shredded, the pieces scattered to the cosmic winds, and the laws of physics forbid you from ever putting them back together. The universe doesn't lose its history, it just becomes unable to remember it. The evidence forces us to confront what physicists call the ultimate fate of computational complexity. In our current universe, complex structures like brains, computers, and ecosystems can process information, create new patterns, generate novelty. But in a maximum entropy heat-death universe, no computation is possible. There are no energy gradients to power processing, no structures to encode information, no temperature differences to extract work from. The universe becomes computationally dead, a state where information exists but cannot be processed, where patterns exist but cannot evolve, where the only computation is the infinitely slow drift of particles through exponentially expanding space. This might be the deepest meaning of heat death, not just the end of energy, but the end of change itself, the end of the new, the end of possibility. So what comes after? Is heat death truly the end, or could something new emerge from the void? This is where physics meets philosophy, where calculation meets speculation, where what we know confronts what we can barely imagine. Several serious physicists have proposed mechanisms by which a dead universe might come back to life, not through magic or wishful thinking, but through the strange implications of quantum mechanics and thermodynamics taken to their ultimate extremes. The most famous proposal comes from Ludwig Boltzmann, who in the 19th century realized something disturbing about thermodynamics. If you wait long enough, random fluctuations should eventually recreate any configuration of matter, no matter how improbable. The implications are staggering. In a heat-death universe at maximum entropy, quantum fluctuations still occur. Particles still pop in and out of existence, and given infinite time, these fluctuations should occasionally produce organized structures purely by chance. Wait 10 to the 10 to the 156 years, a number so large it can't be written out if you used every atom in the universe as a digit, and random fluctuations might spontaneously create a brain with memories of a life it never lived, a Boltzmann brain. Wait longer still, and fluctuations might create an entire solar system, a galaxy, a new Big Bang. This scenario, called Boltzmann cosmology, suggests that heat death isn't permanent. It's just a state the universe spends an incomprehensibly long time in, before random fluctuations eventually kickstart new structures, new complexity, maybe even new universes. But there's a problem, a big problem. If Boltzmann brains are real, if conscious observers are more likely to emerge from random fluctuations than from evolution in a structured universe, then statistically speaking, you are almost certainly a Boltzmann brain. Your memories are false. Your entire life is an illusion that spontaneously formed in the void seconds ago and will dissolve back into chaos moments from now. The fact that you seem to exist in a coherent universe with a long history suggests that Boltzmann brains are somehow suppressed, that the scenario is wrong, or that we're missing something fundamental about quantum mechanics or cosmology. This is one of the strangest problems in modern physics, the need to explain why random fluctuations don't dominate over structured evolution. Other proposals are less paradoxical but equally speculative. Roger Penrose's conformal cyclic cosmology suggests that when the universe reaches a state containing only massless particles at near zero temperature, it becomes mathematically equivalent to a singularity, a new Big Bang. The infinite future becomes a new beginning, and the cycle repeats. String theory suggests that our universe might be one bubble in an eternally inflating multiverse where new universes are constantly being born through quantum tunneling. Our universe might die, but the larger structure persists, generating new physics, new constants, new possibilities. Some theorists propose that vacuum decay, a quantum phase transition to a lower energy state, might eventually occur, instantaneously rewriting the laws of physics throughout the universe and potentially creating new forms of matter and energy we can't imagine. But here's what we actually know, based on evidence rather than speculation. Our universe is evolving from a low-entropy Big Bang toward a high-entropy heat death. The process is irreversible within any reasonable interpretation of known physics. The timeline extends for Google years or more, and we exist in the brief, bright interval when stars shine and complexity flourishes. Everything else, Boltzmann brains, cyclic cosmology, multiverse creation, remains speculative, awaiting evidence that may never arrive. The honest answer to what comes after heat death is, we don't know. We may never know. The heat death itself lies so far in the future that it exists beyond the reach of any conceivable observation or experiment. What we can say with confidence is this: the universe we inhabit, with its stars and galaxies and complex structures, is temporary, precious precisely because it's fleeting. The light exists because it hasn't yet dispersed into darkness. Life exists because energy gradients haven't yet equilibrated. Consciousness exists because the universe is still far enough from maximum entropy to support the complex information processing we call thought. We're witnesses to a cosmic moment that will never be repeated, the brief age when the universe burns bright before its long, slow fade into infinite cold. The question isn't whether the lights will go out. They will. The question is what we do with the light while it lasts. The stars are dying, the darkness is patient, and we are here in this miraculous moment, understanding our fate and finding meaning despite it, or perhaps because of it. The universe is vast, the end is certain, and the story continues, for now.